Okay, Assalamualaikum, very good morning. So let us continue our lecture 5, which is a continuation from Coulomb's law lecture. Previously discussed on the effect of point charge, to the generation of electrical intensity. Okay, so for lecture 5, basically the topics covered will be on the electrical intensity of continuous charge distribution. Okay, in which the emphasis will be on line charge density, surface charge density, and also volume charge density. So basically, we want to find out what should be the value, or how we can calculate the electrical intensity due to effect of line charge, surface charge, and volume charge by applying the Coulomb's law method. Yeah. Okay, so reference for this lecture 5 can be obtained from Sadiku, page 112 to 133. So motivation for this lecture is to calculate the electrical intensity due to continuous charge distribution, which is stated here. Yeah. Okay. So objective for this lecture. So by the end of lecture 5, we want the student to be able to apply Coulomb's law, in calculating the electrical intensity due to line charge and surface charge distribution. Okay, so that should be the aim of lecture 5. Yeah. So from what we have learned previously in chapter 4, in which if we can recall back, basically we have applied the Coulomb's law in calculating the electrical intensity due to a point charge structure. Yeah. So we're going to expand the ideas, we're going to extend the ideas in which the electric field intensity is now is produced by the line charge and surface charge. So how can we modify those methods that we have learned previously in calculating the field intensity due to this charge distribution? Okay, so you can hear my voice clearly, yeah?
Yes, doctor.
Okay, thank you very much for your response. Yeah, so let us proceed with the next slide. Okay, so this is what we have learned previously in chapter 4, in which we have deal with the point charge. So in this particular slide, if we have a point charge Q, in which there is a point of A, which is having a distance of R, from between these two positions, and it is said that unit vector from point Q to the point of A is given by unit vector of R. So it can be said that at this particular location of A, the E field intensity shall be given by this. The E field is given by Q, which is the source of E field, divided by 4 pi epsilon naught of R squared in the direction of R. R squared is, or R itself is the distance between the 2 points, and the vector of R basically can also be returned to be a vector of R divided by R magnitude, in which vector of R basically is the same as this, is the same as this, and we have learned in lecture 1 last time that unit vector is defined to be a vector over the magnitude, the vector is defined to be a vector over the magnitude. This is what we have defined in lecture 1 in the very first lecture of EMT. Okay, so from here we can write that the E field can be further returned to be equals to Q over 4 pi epsilon naught, the vector of R over R power of 3. Okay, so this is the E field due to a point charge which has been calculated by applying a Coulomb's law method. Okay, hopefully you have understand this very well from chapter 4. So now we're going to use this idea into a case whereby the charge of Q is now changed to a line charge structure, surface charge structure, and also a volume charge structure. So what should be the modification that need to be done on the equations of this Coulomb's law that we have seen before? Okay, so that should be our aim, for today's lecture. Hopefully it's clear, Right. So let's have a look. Let's have a a first study on the E field intensity due to a line charge distribution. So imagine that we have a line charge here. Yeah, this is a line charge structure in which the line charge is having a density of rho L. Okay, you have learned this in lecture 3 last time. Rho L is a symbol for a line charge density with a unit of coulombs per meter. Yeah, that should be the units for the line charge density. And we have the length of the line charge equals to L. So the question now is, if we are having this kind of charge distribution, a line charge, and we want to find the E field at this particular location, what should be the value of electric field that will be produced at this point of A? Okay, so that should be our main concern. Yeah, right. So there should be few steps that need to be taken in order for us to find the electric field at the point of A. Yeah. So the first step is we need to identify a small length dl on the line charge itself. Yeah, we need to identify a small length dl on the line charge, and in which we have learned that on this particular dl, there should exist a small amount of charge, which can be defined to be a dq. Yeah. So a dq is amount of charge that is contained in the dl element, yeah, on this particular line charge, in which we have seen this equation before in lecture 3, that the dq and the dl can be returned in terms of this equation, whereby the dq shall be equals to rho L multiplied with dl. Yeah. Okay, so that should be the first step. Step number one is to define the element, the length element, the line element dl, in which we can further define the dq, the charge contained in that particular dl element. Yeah, so that should be the first step. Okay, the second step is that we can then use the dq, yeah, from the first step in calculating the electric field intensity dE contributed by the dq. Okay, so we have seen the equations before for the case of point charge, so I have to rewrite this for you, where we have E field will be equals to Q over 4 pi epsilon naught, the vector of R over R power of 3. Okay, that should be the equations, yeah? We have seen this equation before. So what we did here in step number 2 is that we changed the Q, yeah, we changed the Q to be a dQ. Okay, so in which we are assuming that the point charge is now, I can say, represented, yeah, represented by a continuous charge element, which is a dQ. Okay, and for this particular case, we can say that the electric field intensity produced by this dQ element can be also written to be a dE. Okay, so we can say now, yeah, the migration from our point charge case of Coulomb's law, we have now used that equation in producing the electric field intensity by that particular element of dQ. So in other words, I can see that dQ is somehow assumed to be just a point charge, yeah, just to be a point charge, and as such we can have these equations here, yeah, in which this is the element or the electric field intensity E, a small amount of electric field intensity E produced by the dQ element. Yeah, produced by the dQ element. So we can further write the dQ in terms of rho L dl. So we're going to have rho L dl over 4 pi epsilon naught, the vector of R over R power of 3. So this equation here is similar to this. Yeah, this can be written to be the vector of R over the magnitude of R. The same things. Yeah. Okay, that should be the second step. Yeah. So the first step just now is identifying the dl. We can further obtain the dq, and afterwards we need to define the dE, which is a small element of electric field produced by the dq. And the final step is that in order for us to find the electric field produced by the whole structure, yeah, okay, so what we have here is just a dE, which is electric field produced by a single element here, yeah, a single element here on the dl element. So in order for us to find the E field produced by the whole structure of the line charge, what we have to do, we have to integrate the dE. that we have obtained in step 2 just now. So basically that should be the equations here in which the E total or the total electric field produced by the line charge will be obtained by simply integrating the dE, in which if we further do the integration, the E total will be basically the integrations of rho L dL over 4 pi epsilon naught, the vector of R over R power of 3, in which we are actually integrating the length, the dL element. Yeah, the dL element of this particular line charge structure. So these are 3 steps that need to be taken if you want to calculate the E field intensity due to a line charge distribution. Okay, so if you have any question, you can just ask me during the session. Yeah, right. So let us proceed with the next slide. Okay, this is the case whereby if you are dealing with the line charge distribution or line charge structure, which is a straight line, yeah, we are given a case whereby there is a straight line, a finite length of a line charge structure, in which the line charge structure is extended from a point of A to the point of B. Okay, so the aim of this slide basically is to obtain a general formulation for a electric field intensity produced by a finite length of line charge. Okay, so this is what we want to obtain basically. Yeah, we want to find out, we want to obtain a general formulation for electric field intensity which is produced by a finite length of line charge structure. Okay, so in this particular case, as I mentioned before, we have a line charge having a range from point of A to the point of B with a density of rho L coulombs per meter. We want to find out what should be the value of electric field produced by this structure to the point of A here, in which A is assumed to have a position of R, phi, and Z in cylindrical systems of coordinate. Yeah? So we have understood from our lecture 2 before that in cylindrical system of coordinate, R is defined to be a distance which is a radial distance. Yeah, R is a perpendicular distance. Okay, phi is the angle made between the x-axis with the projection of point A to the xy plane. That should be the phi, while the Z is the height of the point of A from the xy plane. So that's how we define the point of A in cylindrical systems of coordinate. Yeah, so I hope you understand about this representation of point of A. Okay, so I repeat again, R is a perpendicular distance, P is the angle made from the x-axis to the projection of point A to the xy plane, and Z is the height of the point of A from the xy plane. Yeah. Okay. So now, if you want to find the electric field produced by the line charge having a length from A to B to the point of A, so there should be 3 steps that need to be taken as what we have learned in the previous slide. Step number 1 is we need to define, the dl element. So this is your dl element in this purple color. That's our dl element. Okay, so we have a dl. Okay, and the dl in this particular case we use a dz prime, not the dzy. Why use a dz prime instead of z? Because we want to avoid a confusion with the z here. Okay, so z is taken to be a point of A, the height of the point of A. So instead of using a dz for the dl, I'm now using a dz prime, yeah, just to avoid a confusion with the z coordinate for the A point. Okay, that's understood, hopefully. Okay, so on this dz prime element, there should exist a charge amount of dq, yeah, in which dq is written to be equals to rho L dz prime. Okay, that should be our charge element contained in the dz prime length, yeah, of the line charge structure. That should be the first step. So we have done the first step. We've obtained the dl and also the q element. Step number 2 is that we need to define the dE. Yeah, what should be the amount of dE produced by the dq element. So we have to write here that the dE, okay, shall be equals to dq over 4 pi epsilon naught, the vector of r over r power of 3. So we have rho L dz prime divided by 4 pi epsilon naught. Okay, now we have to define the vector of r. Okay, the vector of r. So the vector of r basically should be the vector directed from the dq or from the dz prime to the point of A. That should be our r vector. Okay, that should be our r vector. And if you base on this particular triangle, okay, so I have to redraw the triangle here. That should be our vector of r. So the vector of r basically shall be equals to this vector downwards and this vector which is in perpendicular radial direction. Okay, so for this vector downwards, it should be given by this length, yeah, in terms of the magnitude. So the length for this should be equals to z prime minus z, correct? Z prime minus z, that should be the length. And you know, vector should be pointing downwards, so that should be negative of z direction. Yeah, negative of z direction. Sorry for that. Okay, sorry, I'm using the red color supposedly. Okay, that should be negative z direction for your vector downwards. And for this particular vector, which is similar to this vector, so it should be r, which is the magnitude in the direction of r, yeah? So that should be r direction of positive r. Okay, so for this, I can write that my vector of r should be equals to r direction of r plus z prime minus z direction of negative z. Okay, so that should be my vector of r to be used in this dE equation. So we have to write it here, r a vector of r plus z prime minus z. Okay, direction of negative z. Okay, and in terms of the magnitude of r, it should be r squared plus z prime minus z squared to the power of 3 of 2. Okay, so that should be our dE, which has been obtained, which is produced by the dz prime element or the dq element to the point of A. Okay, that should be our dE. And finally, for step number 3, we can find the total electric field produced by this particular line structure, in which we have to integrate the dE element. So that should be the E field total shall be integrations of the dE here, which is rho L dz prime divided by 4 pi epsilon naught, yeah, r direction, plus z prime minus z negative z direction, divided by r squared plus z prime minus z squared to the power of 3 over 2. So that should be our E total, and the integration, which is based on the integrations toward the dz prime. And it is clear that from this diagram, your integration must be from point of A to the point of B. So that should be the integration in order for us to find the E total. Okay? All right. Is there any question up to this slide? Hopefully you understand, yeah, about this calculation of electric field intensity. So let us proceed with the solution. Okay, I don't want to proceed with this mathematical formulation, but end up I just want to show you that the electric field intensity that will be produced from the integration of these equations here. Okay, the integration for this E total end up will be obtained as shown here in the equations. Okay, that should be the results of the integrations, in which we have the angle of alpha 1 and the angle of alpha 2 produced at the end. So what is meant by the alpha 1 and alpha 2? So basically, I can show you the alpha 1 and alpha 2 position in this diagram. Okay, so this is your point of A, and this is your point of B, based on our previous diagram. And remember, your point of A is here, yeah? That's your point of A, and that is your perpendicular distance, yeah, R. Yeah, R is your perpendicular distance from the line charge to the point of A. If I can recall back, let's have a look at this diagram. That is your R, yeah, perpendicular distance from the line charge to the point of A. Okay, what is meant by alpha 1 and alpha 2? So basically, alpha 1 and alpha 2 is the angle made between the end of the line charge to the point of A. So alpha 1 is taken to be at the bottom part, that should be alpha 1, and alpha 2 should be this upper part of the angle, in which the angle is bounded between the hypotenuse and the R for the alpha 1, and alpha 2 is bounded between the perpendicular distance R and the hypotenuse for the upper triangle. Yeah, so that's how we define the alpha 1 and the alpha 2. Okay, so basically, if we are dealing with the line charge of finite length, yeah, you can obtain the electric field intensity produced by the line charge to any position, any point, if you know three important things. The first one is the R. What is R? R is a perpendicular distance from the line charge to the point of interest. Yeah, remember the word perpendicular distance, so you need to find perpendicular distance from the line charge to the point. Then you need to obtain the angle, both alpha 1 and alpha 2, in which both alpha 1 and alpha 2 are the angle made between the end of the line charge to the point of interest, as shown here in the diagram. Okay, right, so that should be the equation. So you don't have to memorize this equation. This equation will be given. Okay, so you only need to understand how to apply this equation if you are dealing with the line charge, yeah, a straight line charge, yeah, a straight line charge of finite length, yeah. So this equation is only valid for the case of straight line charge of finite length, yeah, of finite length. Okay, so in case if we are having a case whereby we are having a line charge, okay, which is finite initially, which is A to B. Assume that the length of line charge is about, yeah, for instance, let us have a length of 1 kilometer, for instance, yeah, and you need to find a point which is located somewhere here, in which the distance between the line charge to this particular point, let's say the distance is about 1 meter. Okay, this is a perpendicular distance, yeah, between the line charge and the point of interest here. So imagine that we have a 1 kilometer length of a line charge, yeah, 1 kilometer length of a line charge, and a distance perpendicular from the line charge to the point of interest is just 1 meter. So 1 kilometer as compared to 1 meter, so we can assume that the length of this line charge is somehow approaching infinite. Yeah, the length of this line charge is approaching infinite because we compare 1,000 meters, 1 kilometer is 1,000 meters, and compared to 1 meter of length. Okay, so we can assume that the length is somehow infinite. So if we are dealing with this particular case, and if you still want to use the equation previously used, which is E equals to rho L over 4 pi epsilon naught, yeah, R in a vector over R, sine alpha 1 plus sine of alpha 2 plus Z direction over R, cos of alpha 2 minus cos of alpha 1. Okay, remember alpha 1 is down here, and this is your alpha 2. Okay, so if we are dealing with this particular case in which we are assuming that the length is approaching infinite, we can say that the alpha 1, both alpha 1 and alpha 2 are said to be approaching the maximum value, which is 90 degrees. Yeah, that should be the maximum of angle which can be achieved by both alpha 1 and alpha 2. So we can assume that due to the height of the line charge compared to the length of this perpendicular distance, 1,000 meters as compared to 1 meters, we can assume that the line charge is infinite in length, and as such, the angle of alpha 1 and alpha 2 are said to be approaching 90 degrees. So if we substitute this angle into this equation, we can have that the sine of 90 will be equals to 1, sine of alpha 2 will be equals to 1, and this will be equals to 0. And as such, we can going to have E field shall be then equals to rho L over 2 pi epsilon naught of R direction of R in a volt per meter unit. Okay, so this is a simplified version of electric field intensity value if we have a case of line charge which is defined or which is assumed to be infinite in length. So from the equation that we have seen before in the previous slide, which is need to have angle values of alpha 1 and alpha 2 together with the radial distance of R, we can simplify the equations to be just having a single variable of R. Yeah, so this equation can be applied in calculating the electric field intensity, provided that the length of a line charge is assumed to be very, very long. Yeah, so R is maintained to be a perpendicular distance from the line charge to the point of interest. Okay, so this should be the equation that can be applied. Is there any question so far? No, yeah? Okay, let us proceed with this example here. We are given a problems of 2.19 from Hayt book. You are given a uniform line charge of 2 microcoulomb per meter, which is located on the z-axis. We need to obtain the E field intensity in Cartesian coordinate at a point of 1 to 3 if the charge extends from negative infinite to positive infinite, the first case. And second case, if the line charge is extended from negative 4 to positive 4. Okay, let's have a look for the solution for A, which is infinite in length. Yeah, so given that the length is infinite, okay, so let us sketch the diagram first. You see that the line charge is located on the z-axis. Okay, so that's your x, that's your y, and that's your z. Yeah, and the line charge is somehow located here, which is infinite in length. That should be your line charge. Okay, rho L equals to 2 microcoulomb per meter. Okay, you have a point of 1, 2, 3. So you assume that 1, 2, 3 is somehow located here. That's 1, that's your 2, and that's your 3. So we assume that the location of your point is somehow here. Yeah, that's 1, 2, 3. Okay, so since we are having a line charge of infinite in length, so we can straightaway use the equations of E field equals to rho L over 2 pi epsilon naught direction of R and in the direction of R. So we need to use this equation, yeah, to find the E field because your line charge is infinite in length. Okay. So basically, the only variable that need to be obtained here is the R, where R is a radial or perpendicular distance from the line charge to the point of interest. So if you base on this, we can see that your R, your perpendicular distance should be given by this point, in which it will make a 90 degrees length between the 1, 2, 3 point or 1, 2, 3 location with this point on the z-axis. So it is clearly shown that we can define that the point here should be equals to 0, 0, 3. Yeah, that should be the coordinate on the z-axis that will produce a perpendicular distance with a point of 1, 2, 3. Yeah, that should be the location. Okay, and from here, we can straight away find the vector between 0, 0, 3 to 1, 2, 3, in which the vector of R shall be equals to x plus 2 of y. So that should be your vector of R. And following this, you can obtain the magnitude of R simply by calculating the magnitude of the vectors, which is square root of 1 squared plus 2 squared, and that will be given as set of 5. Yeah, so that should be your distance from the point of 0, 0, 3 to 1, 2, 3. And this is also known to be a perpendicular distance from 0, 0, 3 to 1, 2, 3. So we can further write that the equations of E shall be equals to rho L, which is 2 microcoulomb per meter, over 2 pi epsilon naught. R shall be set of 5. Okay, and this unit vector of R can be defined to be vector of R over R magnitude, because the question asks us to find the E field in Cartesian coordinates. So we can have it to be equals to vector of R, which is x plus 2 of y divided by the magnitude of R, which is set of 5. Yeah. Okay. So we can further write that the equations, the unit vector of R type shall be equals to x plus 2 of y divided by set of 5. Yeah, so end up we're going to have 2 micrometer, so 2 microcoulomb per meter over 2 pi epsilon naught x plus 2y divided by 5 in volt per meter unit. Okay, so that should be the E field produced by the line charge of infinite length to the point of 1 to 3. Okay, any question for this example number 1, part A? No, yeah. So let us proceed with this part B of the question, which is we are having a finite length of a line charge. So I sketch the structure one more time. Okay, so that's your X, that should be your Y, and that should be your Z. So we are having a line charge which is having a length from a -4 to +4. Yeah, that should be the length of a line charge given. The line charge is also having a rho L of 2 microcoulomb per meter, and need to find the electric field at the same position, which is 1, 2, 3. Yeah, so that should be 1, that should be 2, and we assume that the location should be somewhere here, 1, 2, 3. Okay, so that should be the point where it would make a 90 degrees angle, or this is a perpendicular distance. So the point here, as what we have seen before, it should be 0, 0, 3. Yeah, and we can say that the distance still set of 5. There's no change for the distance. Yeah. All right. So let's proceed with the equation. So because this is a line charge of finite length, so we shall use E shall be rho L over 4 pi. Okay, rho L over 4 pi epsilon naught in the vector of R over R sine of alpha 1 plus sine of alpha 2 plus Z direction over R cos of alpha 2 minus cos of alpha 1. Okay, that should be the equation that shall be applied in calculating the E field. Okay, so we have defined the R from the diagram. So now let us define the sine and cosine for both alpha 1 and alpha 2. Okay, so what we have to do is that we have to project the end point of the line charge to the point of interest. Yeah, like this, all right? And that should be defined to be the angle of alpha 1. That should be defined to be the angle of alpha 2. Okay? Right, so from this diagram, we can say that this should be the length that shall be used in calculating the sine for the alpha 2, in which the length for this shall be equals to 1 unit. Yeah, and the length for this dimension shall be equal to 7, yeah, because the total length is 8, so that should be 1 and the rest should be 7. So 7 shall be used in calculating the sine for the alpha 1. Yeah, 1 here shall be used for calculating the sine for alpha 2. Okay, so from this diagram, we can also say that the hypotenuse length for the upper triangle shall be equals to set of 1 squared plus set of 5 squared, which will be equals to set of 6 for the hypotenuse. And for this triangle structure downside here, it should be a set of 7 squared plus set of 5 squared, and that should be equal to set of 54. Okay, And for this, we can further define that the E field will be returned to be 2 microcoulomb per meter over 4 pi epsilon naught. R will be defined based on what we have learned before to be equals to x direction plus 2y direction. Yeah, similar to what we have defined before for the R. And R magnitude should be set of 5. Okay, sine alpha 1 will be 7 divided by set of 54 plus sine of alpha 2. Yeah, sine of alpha 2 will be 1 over set of 6. Okay, plus z direction, no changes for the z direction, over the set of 5. Cos alpha 2 will be set of 5 over set of 6. And the cos alpha 1 will be set of 5 over set of 54. Okay, so that should be your electrical intensity produced by this finite length of line charge to the point of 1 to 3 in the units of volt per meter. Okay, so that should be your electrical intensity. So if we compare the E field intensity produced from the previous case of infinite length for part A just now, we can see that your electric field will be very straightforward, very straightforward, very easy to be obtained as compared to the case of E field due to this finite length of line charge, which is a bit tedious in calculating or in obtaining the E field intensity value. Okay, is there any question for this problem? So basically this problem is just to ensure that you understand the difference in calculating the E field for the case of infinite length and also finite length of line charge. Any question for this example? No? Okay, there's no question. Let us proceed with this example number 2, which is we have given the problems of a line charge structure. But the line charge is in the form of circular ring, circular ring, having a uniform charge density of rho L, and the radius of line charge is A, and the axis of the ring is said to be along the z-axis. So somehow we can have, or we can sketch the structure should be look like this, where this is your z-axis, that is your x, that should be your y-axis, and your ring is located somewhere here on the xy plane. Okay, so that should be your ring, circular ring, given that the ring is having a density of rho L coulombs per meter unit, which is a line charge structure, and the radius for the ring is A. Okay, so that should be your structure, the line charge, or the source of electric field. So basically, you need to obtain the E field intensity on the axis, E field intensity on the axis of a ring, in which the axis is on Z. So we need to find what should be the E field intensity produced at any point here on the Z-axis, Okay. So assume that the point here is 0, 0, Z. So Z is a variable, Z is a variable which can be represented to be any point, any point, any coordinate on the Z-axis, So we want to find what should be the amount of electric field produced by this line charge to the point of A. Okay, so because we are dealing with the ring or circular ring or a line charge structure which is not straight, which is not a straight line, so we cannot apply the equations that we have seen before, So what we have to do is that we have to use three basic steps in calculating the E field. Step number 1, as what we have seen before, is to define the element of DL. Yeah, define the element of DL on the line charge structure. So your DL somehow should be located here. Okay, that should be your DL. Okay, and if you base on this particular structure, what should be the appropriate DL to be used here? Anyone? What should be the DL to be used here?
DV.
Okay. Okay. So let's go back to this rectangular structure for your cylindrical systems. Yeah. Okay. Before that, I just want to, we need to choose the appropriate systems of coordinate to be used here in calculating the DL or in calculating the E field. So because your structure is a ring, yeah, it's a ring or it's a circle. So the appropriate systems of coordinate to be used or to be applied here should be a cylindrical system. Yeah, cylindrical system. So for that, let us find out what should be the DL to be used. So for a cylindrical systems, this is a structure that we have produced in our class last week. I mean, in lecture number 2 last time. So in which we have defined that the DL element for this will be dr, for this height will be a dz, and for this curve will be r d phi. So basically, what should be the appropriate DL to be used here? Is it dr, is it dz, or is it r d phi?
R D phi.
R D phi.
Good. It should be r d phi. Yeah. So your DL shall be r d phi. So hopefully you understand. Yeah. That you need to choose appropriate DL to represent the given problems. Yeah. To be substituted in the given problems. Yeah. Okay. So hopefully you understand. Yeah. Okay. Good. So always refer back to this rectangular structure if you have any problems with the DL. Yeah. Okay, but in this particular case, you are given that the radius is given to be A. So what we can do is that the DL here is basically is measured or is sample at this particular curve. Yeah, and the curve is having a radius of A. So what we can do is that we can say that the R shall be further represented or substituted by the A radius. So we're going to have R shall be now equals to A d phi. Yeah, because the actual R value is radius of A. So R should be A then. Yeah. Okay, so we have agreed now that the DL shall be equals to A d phi. Okay, and as such, we can see that on this particular DL, there should exist a charge element of dq, which should be returned to be equals to rho L dl. And we can say that the dq basically should be rho L of A d phi. So that should be the first step. We have obtained the charge element dq on your line charge structure in this particular case. Okay, step number 2. Once you have the dq, you need to find the dE, which is a small amount of electric field produced by the dq element. So that should be returned to be dq over 4 pi epsilon naught, vector of r over r power of 3, which will be returned to be rho L of A d phi over 4 pi epsilon naught. Okay, let us define the vector of r and also the magnitude of r. So r vector, yeah, basically this is a dE. Yeah? dE is directed from this element of dl to this point. Okay, so that should be your dE. Yeah, hopefully you agree with me. That should be the dE, which is a small amount of electric field produced by the dq element or the dl element to the point of interest. So this is our point of interest, yeah, which is at 0, 0, z. Z is any point on the z-axis. So that should be the dE. Okay, so the dE, that should be the vector of dE, which is r. Okay, and the vector of r is actually a combination of this vector, this vector plus this vector. Am I right? So if I need to sketch it for you again, okay, that is your, this is your dl element, that is point of 0, 0, z. So basically that should be the r vector. Okay, so the r vector is equal to this vector plus this vector. So this vector here should be equals to A, the direction of negative R, yeah? Because A is the magnitude and the direction is inward. So that should be negative of R direction, while the vector upward here shall be equals to Z, direction of positive Z. Okay, so we're going to have the vector of R shall be equals to A, direction of negative R, plus Z, direction of Z. Okay, any question for this particular vector R which has been written here? Is there any questions for the vector of R?
Doctor, I got a bit confused that actually the electric field is generated by the line charge along the z-axis or the line charge along the radius A.
Okay, your structure, your source of field here is this rho L. The red color is your line charge, which is the source of electric field. So what we are going to do now is that we want to find out what is the amount of electric field produced by this red line charge to the point of 0, 0, Z.
Okay.
Understood, yeah?
Yes.
Okay, that's why what I did here is first I found the DQ element on the line charge, yeah, DQ element, and afterwards I find the DE, which is a small amount of electric field produced by this DQ to the point of 0, 0, Z. Okay, so that is the things lah, yeah. So we have obtained the electric field intensity produced by a small element of DQ here on the line charge. Yeah, on the line charge of red color. Okay, right. So from the R vector that you have obtained, you can further obtain the distance of R, which is A squared plus Z squared to the power of 3 over 2. Okay, hopefully you understand how can we obtain this one. From the vector itself, we can find that the magnitude will be A squared plus Z squared square root. But since we have a power of 3, so we have 3 to the power of 2. Okay, so that should be the second step, which is the value of electric field produced by a single element of DQ, labeled here. Yeah, remember, yeah? This is just a small amount of electric field produced by a single element of DQ that we have sample or we have obtained here, yeah, in this particular position. Yeah, that should be the amount of electric field produced. Yeah. Okay, step number 3. Once you have the E field intensity produced by a single element, what you have to do, you have to integrate the DE, so that you're going to get the total electric field produced by the whole structure of this line charge of red color. So basically, you have to integrate the DE, which is integrations of rho L A d phi divided by 4 pi epsilon naught A negative of R plus Z, direction of Z, divided by A squared plus Z squared power of 3 over 2. So see that the integration is towards what? It's towards the d phi, which is the integration towards the angle of your line charge. And since your line charge here is a full circle, so your range of integration will be a complete integration or a full circle integration, which will be integration from 0 to 2 pi angle. Yeah, remember the integration is towards the d phi, yeah? Okay, you got the point there, yeah? Okay, good. Okay, one interesting point to be noted here is that if your rho L, yeah, if your rho L here is a uniform, if it's uniform, yeah, uniform means that at any point on the line charge here, the value of rho L is the same. Is the same, yeah. So for instance, at this particular point, the DQ element will be rho L dl. For this element, the DQ element will also be equals to rho L dl. And any point here on the Z, on this particular line charge structure, the DQ will be having a same amount of rho L dl. Okay, so for this particular case, we can say that at this particular DL element, there should be another DL element which is located opposite to it. Okay, this is a DL element which is opposite to this element DL that we have choose earlier. Yeah, we have choose earlier. So this DL and this DL are the same. Yeah, this DL, yeah, this DL, you know, this DL here and this DL here are the same. Okay, in which this DL element will also produce electric field to the position of 00Z. Yeah, it will also produce a DE here, same DE. Yeah, same DE. So what I want to show here is that if I can view the effect of the vector from this side, yeah, from the front side, I'm going to have a position like this. So that should be your DL, that should be your DL, that should be your DL. Okay, that should be your Z-axis, which is 0, 0Z, the point of interest. Okay, so this element of DL or DQ will produce electric field to this position. Sorry, this position. Okay, that should be the R. And opposite to this DQ or DL, there should be another structure which will produce the same DE, the same vector like this. Okay, what I want to stress here is that you can imagine that this vector of R will be having a component of this radius or this radial, and also this component of vectors, and also this component of vectors. Okay, so we can see that when we have two opposite element of DL, yeah, two element of DL which is opposite with each other, we can see that the effect of unit vector of R or vector which is in radial direction, in this case is R, can be cancelled with one another. Am I right? Because the vector is pointing inward and this vector is also pointing inward, so the vector will be cancelled out. Yeah, will be cancelled out. So as such, if we have a case whereby the line charge is said to be uniform, yeah, it's said to be uniform, yeah, in case if the rho L is uniform, then you can have the same effect of this vector which can be cancelled out. But if your rho L is not uniform, so you cannot cancel out the effect of radius. Okay, so if your rho L is uniform, so the effect of R here can be ignored, can be simply put to 0 because of the effect of this cancellation of the vectors. So as such, your total electric field will only be in the Z direction. Yeah, so we can further write the equations here to be equals to rho L A taken out over 4 pi epsilon naught Z direction of Z okay, divided by A squared plus Z squared power to 3 over 2, and we have integrations of the phi from 0 to 2 pi will give us 2 pi. So this can be cancelled out and we're going to have this term. So we're going to have rho L A Z, direction of Z, over 2 epsilon naught A squared plus Z squared to the power of 3 over 2 in the units of volt per meter. So that should be your electric field produced by this particular line charge in a circular ring structure having a radius of A, and the line charge density is uniform with a rho L coulombs per meter unit. Okay, so if you base on that equation, the E field produced will be depending on two main factors. The first one will be your radius of A, okay, and second one will be the distance of Z, distance between or location of your point of interest. Yeah, A is a radius of your line charge, Z is the location or the distance of the point of interest. Okay, so that should be two main point or two main parameters that will affect the value of electric field intensity, apart from the rho L. Rho L is the main factors that will determine the E field. So two main factors apart from rho L, which are the radius of A and also the height of Z or the distance of Z. Okay, is there any questions for this example? No? Okay, let's proceed with next example. Let me see, shall I do this example? Okay, I'm going to skip this one. Okay, you can try to solve this example on your own. Basically, this will be same as what we have discussed before. If you face any problems related to this example, you can ask me personally, yeah, on how to solve for this example. It's straightforward, yeah. So by right, it should there should be no problems of solving this example, yeah. Okay, let us proceed with the example here. We are given a case of uniform line charge density of 5 nanocoulomb per meter located at Y0, Z2 in free space and negative 5 nanocoulomb per meter located at Y0, Z negative 2. Find the E field intensity at the origin. Okay, so we are given two line charge structure. The first one is 5 nanocoulomb per meter located at Y0, Z2. Another one is negative 5 nanocoulomb per meter located at Y0, Z equals to negative 2. So let us sketch the line charge location. Okay, that should be your X. Okay, that should be your Y. And that should be your Z. Okay, so given that your line charge, the first one is at Y0, Z2. Y0, Z2. So what should be the orientation of the line charge then? So line charge supposedly should be located, should be having, or any point on the line charge should be having a coordinate of Y equals to 0 and Z equals to 2. So that's what meant by this equation, in which your line charge supposedly should be straight lined, and this line charge should be parallel with the x-axis. Yeah, so this is 2, location of the Z coordinate. Yeah, and the line charge is 5 nanocoulomb per meter density. So that should be the first line charge. Yeah, and the second line charge will be at 0, Z negative 2, should be this side down here. Again, the line charge should be parallel with the x-axis, because any point on this line charge should be having a value of Y equals to 0 and Z equals to negative 2. Yeah, so that should be negative 2 distance. Okay, so you need to find the E field intensity or the origin at this particular location. Okay, so knowing that there is no information given on the density or the length of the line charge, so we can assume that both line charge, the length of both line charge is approaching infinite. Okay, so that should be our assumption, yeah, because we are not given any conditions on the length of the line charge. So for this, your electric field intensity should be based on this equation, which is E vector or E field should be 2 pi epsilon naught R direction of R. Okay, we're going to have this equation. And since we have two sources of electric field, so the total electric field produced shall be equals to E1 plus E2, which is a principle of superposition that we have learned in lecture 4 last week. Yeah. Okay, so we go for E1. E1 is the electric field produced by this line charge on the top. E2 is the electric field produced by the line charge at the bottom here. Okay, so let us proceed with the first equation of E1, which is rho L over 2 pi epsilon naught R direction of R. Okay, and okay, this is for the second one, rho L over 2 pi epsilon R direction of R. Okay, for the first E1, remember what is R? R is a radial distance or perpendicular distance from the line charge to the point of interest. Yeah, repeat again. R here is a perpendicular distance from the line charge to the point of interest. So basically from here, it is clearly shown that your radial distance of R should be this one. Yeah, so that should be your perpendicular distance, in which the distance should be equals to, it should be equals to 2. Yeah, it should be equals to 2. So you're going to have the equations for the E1 shall be 5 nanocoulomb divided by 2 pi epsilon naught. R has been obtained to be equals to 2. And your vector of R is unit vector directed from this line charge to the point of interest, which is this direction of unit vector. And from this, it is clearly shown that your R shall be equals to negative of Z direction. Yeah. So we're going to have in the vector of R shall be negative of Z direction plus the E field due to the second line charge down here. So that should be your perpendicular distance also, which is 2. Yeah. And the unit vector of R from the line charge to this point shall be equals to Z positive. So we're going to have 5 nanocoulomb negative over 2 pi epsilon naught times 2 direction of positive Z. So that should be your E field total in volt per meter unit. Okay, any question for this example? Any questions so far? No? Okay, if there's no question, let us proceed with the next example. Okay, I don't want to do this example. You can try to do this on your own. Okay, you can proceed with your own on your own on solving this example. Again, if you face any problems, you can consult me on the solutions. Yeah, on your solutions then. Okay, so I'm going to proceed now with another charge distribution, which is a surface charge distribution. So the method is similar to what we have learned before. Yeah, in which there should be 3 steps that need to be taken in calculating the E field intensity due to a surface charge distribution. Okay, the first step will be selecting the DS element. Yeah, that should be the first step, DS element, in which we can obtain the DS. In the DS here, we're going to have a charge of a DQ. Okay, and that should be the first step. And afterwards, step number 2 is that the DQ will produce DE, a small amount of electric field produced by this DS element to the point of B, written to be look like this. Yeah, initially is from the equations of dq over 4 pi epsilon naught vector of r over r power of 3. Okay, this is your DE. Okay, this is your DE. And afterwards, to find the total electric field, you need to integrate the DE, yeah, towards the surface element. So your total electric field will be simply integrations of a DE, in which is integration towards the surface. Yeah, so that should be the 3 steps that need to be taken in calculating the electric field intensity when we are dealing with the source of surface charge distribution or surface charge structure. So the method is similar to what we have learned previously in the case of line charge distribution. Yeah, we just change the DQ to rho SDS. Okay. Any questions for this? Slide. Hopefully you understand. Yeah, it's the same method as before. Okay, let's have a look here. That if we substituted the DQ just now, yeah, DQ equals to rho SDS. Okay, and from here we can find the DE. Okay, the first step, the second step, and the third step is to find the E field. Yeah, that should be the third step. The E field obtained can be written to be look like this. Yeah, which is integrations of rho SDS over 4 pi epsilon naught r squared in the direction of r, or we can also have this as r of r vector or r vector over the magnitude of r. Okay, so This is the equation for the E field, for the finite case, finite area of surface. But what if the surface that we are dealing with is said to be infinite in area? Infinite in area, yeah? Okay, so we need to consider a circular. What we're going to do now is that I'm considering a circular surface charge density of rho s coulombs per meter squared unit with radius of A centered at origin and lying on the z equal to 0 plane. Okay, this is a structure that I'm considering now in order to obtain the equation for the E field due to an infinite area of a surface charge density. Yeah, surface charge density. Okay, yeah. So which means that I have this structure. Okay, that is my z-axis, that is my x-axis, and this is my y-axis. So I'm having, this is my surface charge distribution, rho s coulombs per meter squared, which means that this particular structure, all of it are charges. Yeah, are charges. Yeah, all of these are charges. So what I want to do now is that I want to find out what should be the value of electric field produced by this particular structure to this point. So the point here is on the z-axis, in which we label this as a point of 0, 0, z. So what should be the amount of electric field produced at this particular location due to this surface charge distribution? So that is our aim, yeah? So hopefully you understand. Our aim is to find the electric field due to this particular surface charge structure in which the radius is given to be A, yeah, radius is A, yeah, lying on the xy plane or z equals to 0 plane, and the charge density of rho s coulombs per meter squared. We want to find the E field produced at this location, which is at 0, 0, z. Okay, somehow it is quite similar to the previous example that we did for the case of line charge. But for that example, the charge is only aligned. Yeah, the charge is just on the line. But what we are dealing now is a charge on the surface. Yeah, charge on the surface. It means that all surface here are contained, yeah, or contained with or filled with charges on this particular surface. Yeah? So two different cases here, yeah. Okay, so let's proceed with the solution. So this is what I mentioned before. We have this particular charge structure with the charge of rho s coulombs per meter squared density. Okay, and what we have to do now is to obtain the E field at this position of 0, 0, z. Z is any variable. So the first step that we did is we need to find, we need to choose the ds element. Yeah, ds element. Okay, so ds is taken here. ds is taken here. So we need to choose the ds appropriately. So as what we have learned in the lecture number 2 on the system of coordinate, we need to choose appropriate ds in solving or in representing this ds here. And you go back to this rectangular structure. Okay, this is for cylindrical structure. So we have surface A, we have surface B, and we have surface C. So the question now is which surface ds that shall be used in representing the ds here. Okay, so obviously we need to choose surface of A, yeah, because this is the top surface. So the A is having a value ds which is equals to r d phi or r dr d phi. That should be our ds for this particular surface of A. Yeah, so we need to choose the ds appropriately or correctly. If you choose the surface wrongly, let's say you choose surface C to represent the ds, so the answer will be wrong. Yeah, so you have to be very careful on this selection. Okay, so your ds is equals to r dr d phi, and as such we can write that the dq will be equal to this, yeah, which is rho s ds or rho s r dr d phi. So we have agreed with this. Okay, number 2. This is the first step. Very good. Step number 2 is to find the dE, which is produced by the ds element. So that should be our dE directed in this direction. Yeah, that should be our dE, in which we can write that the dE shall be equals to rho s ds over 4 pi epsilon naught. This is the vector of r, and this is the magnitude of r. This is r power to 3 over 2. Okay, what should be the vector of r here? So the vector of r is this vector, okay, which is the vector in this direction and this vector, correct? So what's the vector here? So the vector here shall be equals to r, direction of negative r. R is a variable. R can be any point between 0 and a. Okay, so r is a variable, yeah? Because your point, your r is located between 0 and a. So you need to choose, you need to use a variable of r to represent this particular point of ds, yeah? Right, and this vector here is z, direction of z. So as such, we're going to have the vector of r to be equals to this, which is r, direction of negative r, plus z, direction of z. And from this r, you can then obtain the magnitude of r to be r squared plus z squared to the power of 3 over 2. Okay. Any question for this? Yeah, any question for this example?
Maybe not related, doctor, but where can we access the recorded session?
I'm asking about this actually the notes, I mean these particular topics, not the recording, not the video recording. Sorry for that. Yeah.
Okay, sorry, doctor.
Any question for this particular problems here? No. Okay. So no question. Let us proceed with the solutions. Okay. Right. So now let us proceed with this E field. So the total E field for our case here shall be integrations of the dE, which is integrations of rho s of r dr d phi over 4 pi epsilon naught. Yeah, r direction of negative r plus z direction of z. Okay, divided by r squared plus z squared power of 3 over 2. Okay. Right. So if you base on this, we have two integrations. The first one is towards the dr, and secondly is towards the d phi. So we have two distinct integrations, yeah, which is integrations towards the radius, yeah, the radius, and integrations towards the angle. Okay. I want to attract your attention to this particular ds element. Okay, so this is the case that we have discussed previously in for the case of line charge in a ring, in which if we have a ds element here, we also have another ds somewhere here. Yeah, in which the ds is said to be the ds is uniform. Yeah, the ds is uniform and located opposite to this ds. So when we have the same ds, similar ds, but located opposite to the initial one, we can see that the effect will be the radius effect, or the radial effect will be cancelled out. So the explanation for this will be similar to what we have discussed previously for the case of ring, yeah, ring line charge. Okay, so for this particular case, we can assume that the effect of vector r can be ignored or can be cancelled out due to the symmetrical effect of those surfaces, yeah, of this ds and this ds. So the effect of r will be cancelled out, yeah. Okay, so we can then simplify the equation to be E field as equals to integration of rho s r dr d phi over 4 pi epsilon naught, yeah, over 4 pi epsilon naught, 3 over 2. Okay, dr d phi over 4 pi epsilon naught z direction of z divided by r squared plus z squared to the power of 3 over 2. Okay, because we have cancelled out the z integration. So now, let us proceed with the integration. It should be integrations of, sorry, yeah. Okay, I should bring it down here. Okay. So we're going to have E field shall be equals to rho s is taken out over 4 pi epsilon naught integrations of d phi, yeah, z should be here, okay. Integrations of r dr divided by r squared plus z squared power to 3 over 2. Okay, so that should be in the direction of z lah. That should be the case. Okay, so what should be the range of phi for this integration? Ihsan Aulia Rahman, can you please help me? What should be the range of integration from for this particular phi?
The range of integration from 0 to R, doctor.
0 to?
R.
R is a distance, right? Your integrations for phi is from this axis
Or the axis.
back to this.
From
So what should be the range
0
of integration? 0 to?
pi.
2 pi. Okay, good. Thank you very much. Okay, Felix, can you please help me? What should be the range of integration for the R here? Felix Tambopolon? Are you in my class?
Yes, doctor.
Okay, can you please help me? What should be the range of integration for the R?
Well, I'm sorry.
Okay, Teo Pei Ting, are you in my class?
Yes, doctor.
Okay, what should be the range of integration for the R then?
0 to A.
Very good. Thank you very much, Pei Ting, for your answer. Okay, that should be the range of integration that need to be taken in order for us to evaluate the value of electric field. Yeah, right. Hopefully you understand from this example. So the phi, because your structure is a circular ring or circular surface, so your phi shall be from 0 to 2 pi, and this is integration for the radius of R. And as I mentioned before, the radius is having a value of A. Yeah, and due to this structure, we know that the R shall be having a range from 0 to A. So that should be the value of the integrations. Yeah. Okay, so if we proceed further, yeah, if I use, sorry for this, okay, I'm going to bring it aside here. So your E field shall be further written to be rho s of z divided by 4 pi epsilon naught. So that will give us 2 pi for the integrations of phi. And for these integrations, we can have it to be equals to -1 over r squared plus z squared power of half. And this is from 0 to A. Okay, this is to be based on the identity, yeah, identity. So there's a special integration for this side, yeah. Right, so if we proceed further, remember there's a direction of z for the E field. If we proceed with the integration, I mean for the solution, we are going to have cancel out of 2 and up, we are going to have the E field in total. To be equals to E field equals to rho s of z divided by 2 epsilon naught. Okay, substitute the 0 and A value in the equations here. So 0 and A shall be substituted to R, yeah, not to Z, because Z is a variable. You need to substitute 0 and A to the R value. So we're going to have the value of 1 over Z minus 1 over A squared plus Z squared power of half in volt per meter unit. So that should be in the Z direction, yeah. I shall put it here, Z direction. Okay. So that should be, sorry. The E field shall be rho L, sorry, rho S, I apologize, rho S, Z over 4 over 2 epsilon naught, okay, 1 over Z minus 1 over A squared plus Z squared power of half in the direction of Z volt per meter. Okay, so this is your electric field equation produced by this particular green structure of surface charge density towards any point on the z-axis, in which if you base on the equation here, the E field will be determined by the rho S, by the surface charge density, by the Z, which is the distance from the surface charge, and also by the A, which is the radius of the surface charge. So these are the parameters that will determine the value of electric field intensity produced by this particular surface charge structure. Okay, so back to our basic question just now, what will happen if your structure or if your surface charge is having infinite in area? Infinite in area. So what should be the changes that need to be done for this particular equation? Quek Chen Pen, are you here in my class? Quek Chen Pen? Oh, I thought you were in my class. Are you having breakfast now? Okay, so for this particular case, we can say that this particular surface charge structure will approaching infinite if the radius of A is said to be approaching infinite value. Am I right? Okay, so the value of A will be approaching infinite. Then we are going to have a case of surface charge structure which is said to be approaching infinite in area. Yeah. Okay, so for this particular case, when A is approaching infinite, then your E field can be further simplified to be equals to E field equals to rho S of Z over 2 epsilon naught of 1 over Z. Yeah, because when we substitute A of infinite in this equation, so that will give us 0. Okay, so that should be in the direction of Z. So we can cancel out the Z and we can then simplify it to be rho S over 2 epsilon naught direction of Z volt per meter. So this is the equation that we have obtained if you are having a surface charge which is infinite in area. So what we have done in this example is that we have obtained the equation for a finite area of surface charge, and afterwards what we did is we extend the idea in which the radius of this circular surface is said to be approaching infinite, and as such we have simplified the equation to be just having this term, which is the E field equation produced by an infinite area of surface charge. Okay then, anyone of you here switch on the mic? Can you please switch off for me? Thank you very much. Okay, that should be the case. Yeah? So we have then simplified to be look like this. So this is the equation. Basically, what we did in the previous example is that, okay, this is your rho S, which is infinite in area in terms of this radius. Okay, the R is approaching infinite. So if your point is located at this position, Okay, this is your Z direction, yeah? I'm using this direction of Z. Okay, so what we did in the previous example is that your point is located here. So the E field at this position will be rho S over 2 epsilon naught direction of Z, volt per meter. But if your point is located down here, okay, so your E field at this position should be E field of rho S over 2 epsilon naught direction of negative Z, volt per meter. Okay, so you can see the difference now, yeah? So if your point is located upward, so your vector, your directional vector should be positive Z. And if your point is located downward, so the value of electric field produced by this surface charge to this point will be in the negative Z direction, which is given in this. So we can then generalize this equation in which it will then return to be look like this, where the E field generated by infinite area of surface charge shall be then returned to be rho S over 2 epsilon naught direction of normal. Direction of normal. So normal means that if the point is upward from the surface, it should be positive. If the point is located downward from the surface, it should be negative direction. Okay, so looking at this equation, we can notice that there should be no effect of a distance. No effect of a distance from the surface charge structure. Yeah, from the surface charge structure. Okay, so hopefully you understand about these topics. Yeah, what we did in these topics, I mean in this lecture. Previously, we have obtained the E field due to a circular surface charge distribution, a finite circular surface charge distribution. We have obtained the equations here, yeah, in which the equations will be based, the E field will be determined by the rho S, determined by the radius of A, and also a distance of Z, yeah, distance of Z from the surface charge structure. But when we extend this idea into infinite area of surface charge, what we did is that we put A to be approaching infinite, and as such, the equation has been simplified to be look like this, where we have rho S over 2 epsilon naught direction of Z, and further on we have generalized the equation to be E field equals to rho S over 2 epsilon naught direction of normal. So there should be no effect of distance, there should be no effect of radius of the surface charge structure. It just depends on the rho S charge density and also the direction of the point, whether it is a positive normal or negative normal with regard to the location of your surface charge density. Okay, is there any question for this slide? No? Okay, let us proceed. Okay, any question? No, yeah? Okay, so let us proceed with this example. Let me see, is there any good examples to be done? No. Okay, let us proceed with examples here. Okay. In this example, this is a very simple example, just to show the effect of the equations that we have seen just now. We have three surfaces, three charge density, which is at 3 nanocoulomb per meter squared at -4. Yeah, at -4. Okay, sorry. We have this charge structure. That's your X. That's your Y. Okay, the first one is at -4 down here. -4. Secondly, is at -1. Okay, it's here, and then we have at +4. That should be the case, yeah. That should be the charge density. We are given that both these three are infinite sheets of charge, yeah. So this is having a density of 3 nanocoulomb per meter squared. This is at 6 nanocoulomb per meter squared, and this is at -8 nanocoulomb per meter squared. Okay. So I just want to do a few examples only. We need to find the E field intensity at this particular points, 4 points given. but I'm going to emphasize at this particular point of C. Point of C is having a coordinate of -1, -5, and +2. So based on this, we can see that the point of -1, -5, and +2 is somehow located here between -1 and +4. So that should be the point of interest, -1, -5, and +2. Okay, that should be the location of your point. Okay, in which we can see that the E field at this position will be then contributed by these three sheets of charge, where we're going to have E field total shall be equals to E1 plus E2 plus E3, because we have three sources of electric field intensity. Okay, let us define that the E1 is due to surface charge at -4, E2 is electric field due to surface charge at -1, E3 is electric field due to surface charge at +4. So we can write that the E1 shall be rho s over epsilon naught or 2 epsilon naught normal direction. E2 will be rho s over 2 epsilon naught normal direction. E3 will be rho s over 2 epsilon naught normal direction. Okay, in which the E1, the E1 be based on this, will be based on this -4. So we're going to have -4 nano over 2 epsilon naught. And normal direction to this particular point of -1, -5, and 2 should be pointing upward. That should be normal direction, yeah? So you based on this, from -4, direction should be positive of Z, yeah? And for the second case, for the E2, which is due to -1, or charge at -1, so it should be 6 nanocoulomb divided by 2 epsilon naught. And the direction of normal should be in this direction also, which is having a direction normal of positive Z. Whereas for the last case, for the third case, oh, this is my mistake again. Sorry for that. It's my mistake, yeah? Sorry for that. Okay. Okay. Right. So the point is here, -1, -5, +2. So as I mentioned before, there should be three contributors of electric field, E1, E2, and E3. Okay. Okay, E3 is due to the charge at -4, which is 3 nanocoulomb over 2 epsilon naught. Normal direction, as I mentioned before, should be Z direction. Okay, positive Z. E2, which is due to the charge at -1, so it should be 6 nano over 2 epsilon naught. The direction normal is also positive Z. While for the third one, E3, which is a charge at 4, so it should be -8 nano over 2 epsilon naught, and normal direction should be downward, which should be -Z direction. So that's how we obtain the electric field intensity due to infinite area of surface charge density. Yeah, infinite area of surface charge density. Okay, we just need to understand, we just need to know what is the direction of normal linear vector from the surface charge to the point of interest. Okay, so please work out for this answer. So that should be your, that should be your electric field intensity in volt per meter unit. Okay, any question for this example? No? Okay, if there's no questions, all right, I don't want to do these examples here. I just want to sketch this example for you. Okay, we are given the annular ring, annular ring with a surface charge density of rho s having inner radius of A and outer radius of B. Okay, somehow your structure should look like this, This is X, this is Y, this is Z, and your structure should be having a ring configuration like this. Okay, imagine that this particular ring, annular ring is located on the XY plane, yeah? Located on the XY plane, yeah? Or the Z equal to 0 plane. Okay, having a radius of A for the inner radius and outer radius of B. Okay, that's how your structure should look like. The question is to find the E field along the Z axis, which is somehow located here, lah. So that should be the point, location, or the coordinate is 0, 0, Z. So if we base on this example, somehow it is similar to what we have done before in the first example for the case of surface charge distribution. Yeah, the difference is that for the previous example, you have a complete charge distribution from 0 to A. 0 to A, radius from 0 to A, a complete charge distribution. But for this particular case, your charge is only exists only between A and B. Yeah, so that should be the place where the charge is said to be contained. Okay. So what we have to do in this particular case is that we have to choose the appropriate range of integration. So if you can recall back from our previous example, we have E field. We have E field equals to rho s over 4 pi epsilon naught. We have integrations of d phi. We have integrations of r dr over r squared plus z squared okay, z squared power to 3 over 2. Okay, so this is obtained from the previous example. Yeah, previous example. For the case of a surface charge which is having a complete radius from 0 to A, yeah, 0 to A. Okay, so for this particular case, your answer end up will be look like this. Yeah, because we are dealing with a similar method, but you have to choose appropriate range of integration in which your d phi, because this is a complete circle, so your d phi will be from 0 to 2 pi. Okay, there should be no problem with that, I believe. But for the range of integration for the r, you have to choose it from A to B only. Yeah, the range of r shall be from A to B, because there is no charge between 0 to A. Yeah, no charge between 0 to A. So I put it here, no charge, yeah, no charge from R between 0 and A. Charge is only exists between A and B. That's why you have to integrate the radius R from A to B only. Okay, so for the rest, I left it for you to solve it. Yeah, then you're going to get the E field for this particular example in volt per meter unit. Okay, so you have to choose the appropriate range of integration to solve this example. Yeah. Okay then. Any question for this example? Okay, hopefully there should be no concern related to this example. Okay, I'm not going to this example. You can try to solve this on your own. Okay, if you have any query related to this example, you can consult me as usual. Yeah. It's a bit complicated, these questions. If I can sketch it for you, this is a case whereby this is Z. Okay, that's X. This is Y. So your structure is should be look like this. Yeah. The X, the charge is located between 0 and infinite. Yeah, 0 and infinite. That should be the range of charge rho s. And y is from negative infinite to positive infinite on the z equal to 0 plane. This is a so-called semi-infinite sheet of charge density. Yeah. So if we can sketch it for you, that should be your charge structure. Okay, so that is your rho S. Okay, so that is your rho S in coulombs per meter squared, which is a semi-infinite sheet of charge. There is no charge for the x equals no charge. So I put it here, no charge for x bigger than 0. Charge is only exists for the case of x less than 0 to negative infinite. So for this particular case, you have to find the E field intensity at a position of A, which is located directly above the edge at x equal to 0. Means that your A is located here on the z-axis. Yeah, that should be the A distance from the edge of at x equal to 0, which is basically located on the z axis, having a distance of A. Yeah. Okay, so for this particular case, if you want to use this equation, E equals to rho S over 2 epsilon naught direction of normal, you cannot use this equation. Because why? Because this is only valid if your surface is infinite in area. But what we have here is semi-infinite. So this equation cannot be applied. So that should be another method, another technique that can be, or that shall be applied in finding the E field at this particular location of A. So please try this at home. Yeah, try this on your own. Have a discussion with your friend. Still, if you have any problems or any ambiguities related to this solution, you can always consult me for further discussion. Yeah. Right. Any question for this example here? Nope. Okay, so for the case of volume charge distribution, it is similar to what we have discussed previously for a case of line charge and volume and surface charge, but I'm not going to cover this in detail because volume charge will be, the E field due to volume charge will be covered in detail in chapter 3 when we learn about the Gauss law. Yeah. So for this particular case, I'm not going to cover the effect of E field intensity due to volume charge distribution. Okay. Right, I'm going to end the class now. It's almost 9:50. So for these examples on the sample test 1, we're going to cover this in our class on Thursday. Yeah. So on Thursday, we are going to solve this example on test 1 questions, previous test 1 questions. And after finish these examples, we're going to proceed with lecture 6, in which we're going to start a lecture on new chapter of EMT, yeah, on the Gauss law. Okay, any questions before we end the class today? Okay, for